Hi, my name is Dear Tiagi, and in this video, I'll be going over Gauss's law and electric flux for AP Physics C. So to start, what is electric flux? So electric flux is defined as the amount of electric field going through a certain area. And so if we're looking at it visually, electric flux is equal to, we're just looking at it visually, we have a plane, for example, call it of area A, and we have electric field going through it, E. So flux, which is given the symbol phi, is equal to the amount of electric field vectors going through this area A. And so mathematically, the way we define it is as the dot product between the electric field and the area. And visually, this should make some sense, right? If you know a plane, with a plane, the vector is defined as the vector perpendicular to the plane. So this vector here is going to be our A vector, and this vector here is going to be our E vector. And so we know that the dot product is equal to the magnitude of E times the magnitude of A times the cosine theta, where theta is the angle between the two vectors. And so when we have a plane that's like this, right, it's completely perpendicular to the electric field, we can see that the vector A and vector E are parallel. Because they're parallel, the cosine theta equals 0, and therefore it equals EA, which makes sense because this is the maximal rotation of the A plane such that we get the most amount of electric field, which you can imagine is like water, going through the plane. On the other hand, if we have a plane that looks like this, so if we rotate it 90 degrees, our A vector is going to be out like this, and then our electric field lines going up. Maybe I shouldn't draw on that, but our electric field lines are going up, right? And so the angle, right, so if we have A this way, E this way, our angle is 90 degrees. EA cosine of 90 degrees, cosine of 90 is 0, which equals 0. And this makes sense because if we have a plane perpendicular and our electric field is going like this, right, you're not going to have any kind of flux because it's not actually going through the plane. Okay, so that's electric flux. Now we can get into Gauss's law. So Gauss's law states that the total electric flux going through a object, so the total flux is equal to the total charge that's enclosed by the surface over the permittivity of free space, or epsilon naught. And so epsilon naught is equal to 8.85 times 10 to the negative 12, and that's just a constant. And so the way we write this, the left-hand side, the electric flux, we write it as the closed integral of E dot dA. That equals Q enclosed over epsilon naught. And the reason why is because when we're dealing with Gauss's law, we're usually not going to have just a straight plane, right? So if we have, for example, a curve like this, right? If we have an electric field going like this, right? So here, the angle's changing. We have different A vectors, because we have A vector here, like so, A vector like here, A vector here, A vector here, A vector here. So the A vector is changing. And so the way we can actually find the total flux then in the situation, because it's a curve, is we have to take the integral. So we take tiny dAs, we measure how much electric field is going through those tiny dAs. So in other words, we're taking the integral of E dot dA. And the reason why we have this symbol, this little circle, on the integral, that's called a closed integral or a line integral. And the reason why is because dA is changing in terms of dx and dy. So we're changing in 2 dimensions. And so therefore we have this closed integral, or this symbol, to show that we're integrating over a surface. So that's Gauss's law, and this left-hand side is really symbolic. It's not actually meant to be ever evaluated, so you never actually need to do a line integral in Physics C. And the way it's symbolic, the reason we're able to make it symbolic, is by creating a thing called a Gaussian surface. So a Gaussian surface, just erase this, is a surface, a 3D surface that encapsulates an object and matches the symmetry of it. So for example, if we have a circle, the Gaussian surface's symmetry, this thing, would be a circle around it. And the reason why, now if you imagine, is that if the electric field is here and we take a dA, that dA at that point right here is going to be straight, and it's going to be perpendicular to here too. So it's perpendicular, perpendicular, which means that E dot A, the dot product, is just going to equal EA, because we're using a surface, a symmetry, such that our EA, our E and the A vectors are always going to be parallel because of the symmetry of the shape. So we're using Gaussian surface such that we're matching the symmetry of the shape. Okay, and so if we think about the integral, right? So we take an integral of EA. So we'll actually we're taking an integral of E dot dA, right? Because this is equal to E dot dA cosine theta, and we know our cosine theta is going to be 1 because cosine of 0 is 1, and we know it's 0 because we chose Gaussian surface such that it's 0. This is going to equal just EA because E is a constant. We pull it out. dA is just going to equal A, so EA is the evaluation of this. And so whenever you get this, usually what's going to happen is this is just going to become EA equals Q enclosed over epsilon naught, and then you just solve for E based on this equation. But it is important that you write this. This is like the first step. Then you can go to this part after you make a Gaussian surface such that you match the symmetry of the object. And finally, let's just go over the 3 types of charge densities that you need to know for these kinds of problems. So the first type is called linear charge density, given the symbol lambda. So linear charge density is equal to the amount of charge, Q, per unit length, L. Then we have surface charge density, sigma, which is the amount of charge per unit area. And then we have volumetric charge density, given the symbol rho, and it's amount of charge per volumetric, or per volume. And those are the 3 types of charge densities that you need to know for Gauss's law. So to start, let's do some problems and some derivations. So we'll start with conductors. So again, a conductor is a metal that allows charge to go through it, and therefore it's evenly distributed inside. So we don't have a rho because the charge is evenly distributed, so there's no rho in there. So let's start with a sheet, for example. Let's say the sheet has charge Q, and we're looking for the electric field. So Gauss's law, right? So E dot dA equals Q enclosed over epsilon naught. So we're going to create a Gaussian surface such that the electric fields are always going to be parallel to our area vector. So in this case, the Gaussian surface I'm going to choose is a cylinder. We could have also chosen a box, it doesn't matter, but we chose a cylinder, like so, right? So here, this is my area, A, right? So the E dot dA, the dA stands for the area of the actual Gaussian surface. So my area is right there. The area on the sides doesn't matter, right? Because the electric field from a plate is just going to be, perpendicular to the plate. There's no electric field going sideways, so there's no field here or here. It's just up and down. So E dot dA becomes E times area total equaling Q enclosed epsilon naught. So what is our area total? Since we have electric field going this way, right? We have an area here, A, but we also have the electric field going below it too. So we have electric field like this, and this is also A2. So our area total is equal to 2A, so E times 2A is equal to Q enclosed epsilon naught. What is our Q enclosed? Well, we know that the surface charge is equal to Q over area total. Q is our total charge. And so our Q enclosed is going to equal to Q enclosed over area enclosed. Our area enclosed is just A, so Q enclosed A. Q enclosed therefore is equal to surface charge density times A. If we plug that in, surface charge density A over epsilon naught, the A's cancel out, and we get that E is equal to surface charge density over 2 epsilon naught. Okay, next one, let's go through a sphere. So let's say we have a sphere. I'm just going to draw a circle because you can't really draw spheres on 2D. But let's say we have a sphere, like so, charge dense of Q. And we're looking for the function, electric field, as a function of R. So in this case, we have to create 2 Gaussian surfaces because we have 2 situations. We have the situation that where R is inside the sphere. Let's call it the radius, big R. So we have a situation that the little r is inside the sphere, and we also have a situation that it's around the sphere. So 2 Gaussian surfaces, call this 1, call this 2. So let's start with case 2 first. So with case 2, again, integral of E dot dA is equal to Q enclosed epsilon naught. Since we chose a good Gaussian surface, it's just E a Q enclosed epsilon naught. Our Q enclosed is just going to be Q, right? Because our Gaussian surface is enclosing this entire sphere. So just Q epsilon naught. So the A, right? So how much area is our Gaussian surface. So the area of our Gaussian surface is equal to, this is going to be r, right? So we're doing a function of r. So e 4 pi r squared q epsilon naught, and therefore our electric field is equal to q over 4 pi squared epsilon naught, which you can notice is just a point charge, which makes sense because it's a sphere. Next, let's do case 1. So with case 1, what we have is, again, we have the same integral stuff, right? So make sure to write that. But we have that EA is equal to Q enclosed over epsilon naught. Okay? So the question is, do we have an electric field inside, if you imagine, inside the sphere? And the answer is no, we do not have electric fields. And the reason why we don't have electric fields inside the sphere is because when we're inside a sphere, there is no charge being circulated. And if there's no charge being circulated, there is no electric field, right? Because electric field is part of force, right? F equals QE. And so if we have no electric field, there's going to be no charge circulation because of this. And so therefore, what scientists have realized is that there's no charge circulation inside a conductor. And so therefore, there's no electric field. And because of that, this term, E, becomes 0. So left-hand side is 0. Now epsilon naught cannot be 0, right? It's constant, which means that our Q enclosed has to be 0 to match the left-hand side. So Q enclosed is equal to 0. And this is a very powerful statement because what it suggests, it says that any conductor, so we have a conductor like this, in this case, right, all the electric charge is on the outside. So all the excess electric charge is here, concentrated on the outside. So inside, it's neutral. So neutral inside, all the charges on the outside. And this is actually a generalization that can go with any conductor. So if we have like a weird shaped thing here, right, it's a conductor, all the electric charge is on the outside, and the inside is neutral based on this statement. So there's never going to be any electric charge inside a conductor. It's all going to be on the outside. So those are conductors. Now let's just go through a couple examples of insulators. So an insulator is obviously something that prohibits electric charge from circulating and going around. And so the first thing we're going to look at is we're going to look at a sphere, again, with radius r, and it's going to have Q that's evenly distributed. And again, we have two cases, case 2, case 1, right? Case 2 is pretty trivial again. It's just going to be EA is equal to Q epsilon naught. Q is our total charge, right? Because we're circulating the entire sphere. And so E is just equal to the formula for a point charge. But what about case 1? Okay, so case 1 is going to be a sphere like that. So here we have that E times A is equal to Q enclosed over epsilon naught. So the question is, do we have an electric field in this situation? And the answer is, when we have an insulator, there can be an electric field inside the insulator. And the reason why is because when we have an insulator, the electrons or the electric charge is not able to move. And so because of that, the charge isn't able to kind of become neutral inside because it's not able to move. It's like stuck. And because it's stuck, we're allowed to have an electric field inside even if there's no charge being circulated because, again, insulators prevent electric charges from moving. So EA is equal to Q enclosed over epsilon naught. So we know that A is going to be obviously 4 pi little r squared over Q enclosed epsilon naught. But what is our Q enclosed? This is where we have to use the volumetric charge density. So volumetric charge density is equal to Q total over V total, right? And so for our Q enclosed, it's going to equal to Q enclosed over volume enclosed. So Q enclosed is equal to rho, the volumetric charge density, times volume enclosed. Now our volume enclosed is going to be just a volume formula, right? 4/3 pi r cubed. So we plug it in, we get that E 4 pi r squared is equal to rho 4/3 pi r cubed over epsilon naught. 4 pi cancels out. The r's cancel out, and we get that electric field is equal to rho r over 3 epsilon naught. And from here, if we want to get it in terms of Q, what we can do is we can say, okay, well, rho is equal to Q over volume total, which is 4/3 pi big R cubed. And then we can just plug it into here. And if we plug it in, we'll get electric field is equal to Q 4 pi big R squared epsilon naught times R. And that's if we want to just get in terms of Q. Okay, let's do another situation. Let's say we have another sphere, so kind of similar. But let's say we have another sphere. So radius R, big R. But this time, instead of having a Q that is evenly distributed throughout, we're going to have a function for the volumetric charge density. So a function, rho of R, is equal to alpha R. So alpha is just a constant, don't mind that. But basically what it's saying is that as our R increases, we're changing the amount of volumetric charge in that space by this function. Okay, so let's do case 1 first. Case 1 is going to be where R is less than big R. And so the integral E dot dA over Q enclosed epsilon naught, right, so this becomes EA because we're choosing a Gaussian surface. That's a good one. Over Q enclosed epsilon naught. So we know again that our area of the Gaussian surface is going to be 4 pi little r squared. But what is our Q enclosed? So here's where we have to use the volumetric charge density again. So we know that rho is equal to Q over V total, right? Which is also equal, therefore, to dQ over dV. Because again, we're just taking ratios between Q and V. If we multiply both sides by dV, we get that dQ is equal to rho dV. And if we integrate that, we get that Q enclosed is equal to the integral of rho dV, where we have bounds for the surface we're creating. But the issue is our function, rho of R, is equal to, in terms of R, right? It's not in terms of V. And so we have to get this dV into a dr. So we know the formula for a sphere is equal to, volume is 4/3 pi r cubed. And so what I'm going to do is I'm going to use implicit differentiation to get it into dV. So if we take derivative, we get a dV is equal to r cubed becomes r squared. So 4 pi r squared dr. And so now we can plug this into here. If we can plug this into here, we can plug them both into here. And we get that Q enclosed is equal to the integral. 4 pi and alpha are constants, so we can take those out. So 4 pi alpha, integral of r squared times r, so r cubed, and then dr. So if we integrate that, and we're integrating, again, Q enclosed is from 0, right, 0 to the center, to r, little r. So we're integrating from 0 to r, little r. So 4 pi alpha r to the power 4 over r from r to 0, 0 to 0. So we get that the answer is the Q enclosed is equal to alpha pi r to the power 4. We plug it in, so alpha pi r to the power 4 over epsilon naught. Solve for E, we get that E, the electric field, is equal to alpha r to the power 4 over 4 epsilon naught. Okay, so now let's do one more situation, or not more situation. Now let's find the electric field outside of the sphere. And this one isn't as simple as the ones we've been doing before. Again, the reason why is because we don't know what Q is, right? We don't know our total Q. So if R is greater than uppercase R, what is our electric field? So same steps, right? EA, Q enclosed over epsilon naught. But the only change, the same exact steps here, the only change is that instead of this being little r, our bounds are going to be big R. And so this becomes 4, or a pi r, big R to the power 4. Okay, so we plug it in, so E 4 pi little r squared is equal to a pi big R to the power 4 over epsilon naught. The pi's cancel out, and we get the same kind of similar thing. We get the electric field is equal to alpha big R to the power 4 over 4 epsilon naught times 1 over little r squared, and that's the formula for our electric field. And yeah, that's Gauss's law for conductors and insulators, and that's electric fields, or fluxes, sorry. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.